Well, hello everyone, welcome to the European Non-Associative Algebra seminar. Today's talk is by Buzaglo from the University of Edinburgh, United Kingdom. The title of his talk is Derivations, Extensions, and Rigidity of Subalgebras of the Witt algebra. Please.
There we go. Yeah, thank you very much for inviting me to speak. So I actually only found out I was giving the talk today a few hours ago. So I apologize if the talk is not very good or not very well prepared. I've only had a few hours to prepare, so I hope it's okay. But yeah, anyway, so I'm going to talk about some of my work that appeared on the archive last year, and it should appear in the Journal of Algebra at some point in the near future. So yeah, the outline of the talk is that first I'll give some motivation as to why I started thinking about this problem. Then I'll talk about a computation of derivations of some Lie algebras, then about a computation of extensions, and then finally something, well, I've called it rigidity, but yeah, I'll explain what I mean by that later. Okay, so throughout the talk, there's some notation that I'll fix. So A is always an associative algebra over the complex numbers. L is a Lie algebra also over the complex numbers. And M is a representation of L. So usually I'll take M to be the trivial one-dimensional representation, C, or I'll take it to be the adjoint representation most of the time. And yeah, so a derivation of an associative algebra A is a linear map from A to itself, which satisfies the Leibniz rule down here. So it's just a generalization of the product rule that we're all used to. And dir A denotes the set of all derivations of A. And this is a Lie algebra with this bracket. So actually, if you take two derivations D1 and D2 and you compose them together, in general, that's not a derivation. But if you take the commutator, that always satisfies the Leibniz rule. So it's a Lie algebra, but it's not an associative algebra. Okay. So yeah, what is the Witt algebra? So in this talk, I'll mainly focus on actually the one-sided Witt algebra, but I've defined both of the algebras, the Lie algebras here. So the one-sided Witt algebra is W1. It consists of derivations of the polynomial ring in one variable. And actually it turns out that every derivation of the polynomial ring in one variable is of this form. So what I mean by this notation, CT del, well, del is derivation with respect to t. But what I mean by this is that every derivation of the polynomial ring in one variable, well, will be denoted by f del, where f is some polynomial, and it acts on the derivation on some polynomial g is just sort of the obvious thing. So it's f g prime. So every derivation of the polynomial ring in one variable consists of first we differentiate the polynomial and then we multiply by some other polynomial. And then similarly, the Witt algebra is the algebra of derivations of the Laurent polynomial ring. So in this case, t is invertible, and it has a very similar description. Again, it's just Laurent polynomials times this operator del. Okay. So yeah, the Lie bracket in the Witt algebra is given by this equation. So f del, the bracket of f del and g del is f g prime minus f prime g times del, where these are polynomials. So I guess one of my motivating questions is to study subalgebras of the one-sided Witt algebra and the full Witt algebra. So for example, can we classify them? Are there any nice properties that they have? So this gives a very nice, interesting source of some infinite dimensional Lie algebras, which is something I'm interested in. And in this talk, as I said, I'll only really talk about W1, but almost all the results that I'll mention are true for the full Witt algebra, just with the obvious changes. The changes being, when I have fg in the polynomial ring in one variable, instead of saying that, you just say in the Laurent polynomial ring. Those are usually the obvious changes that you have to make. Okay. So now I'll talk about these, a big class of subalgebras of the Witt algebra, or in fact of any Lie algebra derivations. So if we have, I guess here I should say that A should be commutative algebra. So if A is a commutative algebra, then the Lie algebra of derivations of A is naturally a module over A. If we take some derivation of A, then it's just sort of the action of A on D is sort of the obvious thing. So A acting on D evaluated at B is just A times the derivation evaluated at B. And I call a submodule subalgebra is just a Lie subalgebra of this should say dir A. Sorry. Can there be some typos? Dir A, which is also a submodule with the action of A. And in the case of W1, these have the following form. So I'll denote them by F times W1, where F is some polynomial. So they just consist of elements of W1 which are divisible by this polynomial F. So all submodule subalgebras of W1 are of this form. And one question we might ask is, so given two polynomials F and G, when are the submodule subalgebras they define isomorphic, just as Lie algebras? And so to answer this question, well, the most obvious way in which they can be isomorphic is if we just take some automorphism of W1, then FW1 is isomorphic to the image of FW1 under this automorphism phi. And actually it turns out that you can check pretty easily that the image of a submodule subalgebra under an automorphism of W1 is still a submodule subalgebra. So here we have two submodule subalgebras which are isomorphic, kind of in a boring way. But I conjectured that this way, so just restricting automorphisms or just evaluating submodule subalgebras on automorphisms of W1, this is the only way in which two submodule subalgebras can be isomorphic. So in other words, if we have an isomorphism between submodule subalgebras, then phi is a restriction of an automorphism of W1. So it extends to an automorphism of the full Lie algebra. Yeah, so this is the conjecture just restated again. And sort of this behavior, it led me to believe that there's some sort of rigidity going on in the sense that the Lie algebraic properties of subalgebras of W1 are controlled by W1. So there are no sort of weird isomorphisms between submodule subalgebras, for example. And sort of the goals that I set out for myself and sort of the goals for what I'll cover in this talk is, so the first one is to prove this conjecture. And the second is to explain this rigidity. So come up with some reason as to why submodule subalgebras exhibit this rigidity. And so the first goal I accomplished. So it's a theorem from last year. So this is now a theorem, and I'll explain sort of how the proof goes in this talk. Okay, so the idea for the proof that I had, and in fact it does indeed work, is that is to remove so we start with submodule subalgebras FW1 and GW1, and there's some isomorphism between them. Then the idea is to remove a root of F and a root of G. So, and then hope that this isomorphism extends to an isomorphism after removing the roots. So just, yeah, basically choose some whatever root of F you like, divide F by t minus x, so just remove the root. And then there should be some appropriately chosen root y of G, such that this isomorphism extends in this way. And my notation here, VF and VG are just the vanishing loci of F and G. So this is the set of roots of F and the set of roots of G. Okay. So what this leads to is that I want to study one-dimensional extensions of submodule subalgebras. So I want to, so that FW, this should say FW1. So FW1 has codimension 1 in this Lie algebra where we'd removed one of the roots. So I'm studying one-dimensional extensions because this is sort of going up one dimension. And I want to do that in order to be able to say that this isomorphism extends. So that's sort of the motivation to study these extensions. And so, yeah, and this is a short exact sequence, and this sort of the sort of set of all short exact sequences of this form, where there's something this might not be the same thing in the middle, but yeah, just replace this with say replace this with just some x or something. So the set of all short exact sequences of this form where there's some x in the middle, it corresponds, there's a one-to-one correspondence between the non-split exact sequences of this form and the x group, this x group here, where M is some one-dimensional representation of FW1. And so that's what led me to study this object here. And sort of the first case that we should look at is where M is the trivial one-dimensional representation. So let's do that. But I guess, yeah, so this is going to correspond to derivations. So if we have a Lie algebra L, a derivation of L is sort of the same exact definition we have for associative algebras, but instead of the multiplication of associative algebra in an associative algebra, we just have the Lie bracket. So again, it's just a linear map from L to itself, which satisfies the Leibniz rule. So we apply D to Y in the first one, and then D applied to X in the second one. And the derivation is called an inner derivation if D is add of X, where add X of Y is just the bracket of X and Y. So add X, this the set of inner derivations consists of just derivations of the form add X. And so it turns out that this X group, where we take in the first position, we take the trivial one-dimensional representation, that is actually isomorphic, or I guess you could define H1 of L with coefficients in L to be this X group. And it is turns out to be isomorphic to this sort of outer derivations. So derivations of L modulo inner derivations. So I guess that our first goal is to compute this cohomology, or equivalently compute derivations of submodule subalgebras. So we've gone from this problem of when are two submodule subalgebras isomorphic to this sort of short exact sequences perspective, and then starting with the easiest case where the module is trivial, we're now ending up with wanting to compute derivations. So that's the first step, is to compute derivations. So that's what so that's the question I'm asking. What do derivations of submodule subalgebras look like? Well, there's some obvious ones. So if we take some element of W1 such that add of W acting on FW1 stays inside of W1, then if we restrict this adjoint action of little w to the submodule subalgebra, then we get a derivation of FW1. So I guess the question you might ask is when does this inclusion hold? And okay, here I said if W is G del, so G is just some polynomial, then we need the bracket of F del and G del. So we need this, basically this polynomial here, Fg prime minus F prime G, to be divisible by F. That is what it means to lie inside FW1. We need this polynomial here to be divisible by F. And sort of a very easy lemma is that if we have two polynomials and here X is a root of F, well, if X is not a root of G, so if X is a root of F but not a root of G, then the order of vanishing goes down by 1 when we take the bracket with G. So when I write ord X, I mean the order of vanishing of a polynomial at a particular point. So for example, ord 0 of t to the 4 or whatever is 4. So yeah. So yeah, the order of vanishing goes down by 1. What happens is because we want this polynomial to be divisible by f, well, if g doesn't vanish at this root, then if g doesn't vanish at the root x, then the order of vanishing is too low. So this polynomial, this bracket will not be divisible by f if gx is not 0. So what we've concluded is that if we want this to be divisible by f, then we need g to vanish at all the roots of f. So yeah, we need this element w to vanish at all the roots of f. And so what this means is that w must be in the submodule subalgebra defined by rad f, where rad f is the radical of f, just consists of a polynomial which vanishes at all the roots of f. So for example, if we have let's take the rad of t to the 5 t minus 1 squared or something, and this is just basically we just take exactly the same polynomial, except we just put all the exponents to be 1. So that's the radical of t to the power 5 t minus 1 squared. It's just t times t minus 1. Yeah, so we need that. And actually, this turns out to be all derivations. So if we have some submodule subalgebra FW1, then its Lie algebra derivations just consists of the adjoint action of little w, where little w is an element of rad f W1. So yeah, basically w needs to be divisible by, it needs to vanish at all the roots of f. That's the only condition there is, and actually that's the only type of derivation we get. So in other words, or in particular, the Lie algebra derivations of FW1 is isomorphic to this submodule subalgebra rad f times W1. And we can calculate the dimension of H1. So it's just the degree of f minus the degree of the radical. So in particular, if f is equal to its radical, so if f is a reduced polynomial, if f only has roots of order 1, then this is 0. F is equal to its radical, so this is going to be 0. And in that case, so I guess I should maybe write that. So if f is equal to its radical, then H1 this is 0, and in this case, this submodule subalgebra is actually a complete Lie algebra. It's not too important. Not too important what that means for the purposes of this talk, but if you're interested in those kinds of properties, then it's known. It's what's known as a complete Lie algebra. Okay. So maybe, are there any questions so far about this? Okay. So actually, there's an even stronger result than what so I've kind of undersold my result. So as I've written here, submodule subalgebras have finite codimension in W1 because the codimension is equal to the degree of f, which is obviously a finite number. And actually all, I should say, this should say finite codimension. All finite codimension subalgebras of W1 are essentially submodule subalgebras in the sense of this theorem. So if we have some subalgebra of W1 of finite codimension, then it's nested between two submodule subalgebras in this way. So there is some f such that this inclusion holds. So they're very close. Every subalgebra of finite codimension is very close to being a submodule subalgebra. So that means we can extract a lot of information about general subalgebras of finite codimension just from looking at submodule subalgebras. And actually, even more is true. If we have an infinite dimensional subalgebra of W1, so not necessarily even a finite codimension, this could be even infinite codimension, then still it is very closely related to a submodule subalgebra because of the following theorem, which says that if we have an infinite dimensional subalgebra of W1, then it is isomorphic to something of finite codimension. And then by the previous theorem, we know that it's therefore closely related to a submodule subalgebra. And just as a warning, this is not true for the full Witt algebra. So some of the stuff I'm going to say on this slide is not true for the Witt algebra, but it is true for the one-sided Witt algebra. Great. So thanks to this theorem and the theorem on the previous slide. So yeah, I should say this theorem is joint work with Jason Bell from the University of Waterloo. So yeah, it turns out that the Lie algebra derivations of this infinite dimensional subalgebra again consists of these this add of W, where W is some element of the one-sided Witt algebra, such that the bracket, when you take the bracket of W and any element of L, that still lies in L. So again, it's sort of the most obvious. I mean, it has. So I mean, this inclusion is obvious, and it's sort of the other inclusion that's not the obvious one. So yes, it turns out that all derivations of L are restrictions of derivations of W1. As a consequence, the Lie algebra derivations of L is isomorphic to the normalizer of L in W1, and therefore the this cohomology H1 of L with coefficients in L is isomorphic to the normalizer modulo L. So that's great. Now, maybe I guess before we move on to extensions, any questions about that? So we've kind of completed the derivation story. Great. So yeah, as I said, we've just done this X group. We've just computed the X group where we have a trivial module in the first coordinate. So now let's generalize that. Let's look at an arbitrary one-dimensional module M in the first coordinate. So this corresponds to short exact sequences of this form, where we have FW1 in the first slot, M in the second slot, and then just some X in the middle. And the key idea here is that if we have a one-dimensional representation of L, then this is actually going to be trivial as a representation of the derived subalgebra. And this is kind of, it's quite easy to show. So if we have, say M is just CA, say it's one dimensional, then if we take XY acting on A, then this is X acting on A minus Y acting on A. And sorry, that's not what I meant at all. X acting on, there we go, Y acting on A minus Y acting on X acting on A. Say Y acting on A, okay, say X acting on A is lambda A, and Y acting on it, because it's one dimensional, it's just going to be scalar multiples of A. So now this is going to be lambda times mu of A times A minus mu times lambda times A. So this is 0. So basically, the action of any bracket acting on the one basis element of M is trivial. So it's a trivial module over the, if M is one dimensional, then it's a trivial module over the derived subalgebra. So if we view this short exact sequence up here as a short exact sequence of representations over the derived subalgebra of FW1, which is F squared W1, that's quite an easy thing to show, then this actually looks like this. So it's it looks exactly the same, except in the last coordinate I've just changed m for c because it's trivial as a representation of f squared W1. And so this gives me an element of this X group where we have a C in the first coordinate. And so this is sort of this group of outer derivations. This what I mean by this like comma FW1, it just means the sort of derivations of F squared W1 whose image lands in FW1. So it's like an element here in this derivation thing is a map from F squared W1 to FW1. Satisfying the Leibniz rule that from a few slides ago. So slightly different to the derivations that we computed before, but it's essentially the same. It's a very similar computation. So we basically know this, even though I haven't really said it explicitly. We basically do know this from our previous stuff on derivations. So thanks to that, we have this proposition. So if we have some Lie subalgebra of finite codimension, and we have a one-dimensional extension, and yeah, what I mean by one-dimensional extension is just we have this short exact sequence that is non-split, and the dimension of this last thing, L bar mod L, is one-dimensional. So this last thing has to be one-dimensional. Then this L bar, this one-dimensional extension, can be uniquely embedded in W1 such that this diagram commutes, where this arrow on the top is just sort of the natural inclusion of L into W1. And this is this inclusion here is just the inclusion from the short exact sequence. And sort of the, yeah, so one-dimensional extensions of finite codimension subalgebras of W1 very naturally live inside, they're contained inside W1. So if we do this process of doing one-dimensional extensions, we're always staying inside W1. So again, this is sort of some other, it's another instance of this sort of rigidity. And yeah, as I said, the proof kind of follows by looking at these short exact sequences as short exact sequences of representations over the derived subalgebra. And then we can use our results from derivations that I talked about earlier. Great. So yeah, as I said, one-dimensional extensions are contained in W1. But this was for arbitrary subalgebras of finite codimension. The result on the previous slide. But if we take some explicit subalgebra, say a submodule subalgebra FW1, can we compute one-dimensional extensions explicitly? So what are some obvious one-dimensional extensions of FW1? So on the one hand, we have derivations. So if we have a non-reduced polynomial, so the radical is not equal to the polynomial, then we can take any element W, which is in the submodule subalgebra defined by the radical, but not in the submodule subalgebra defined by F. So that is, this is a polynomial which is divisible. So it vanishes at all the roots of F, but the order of vanishing is too low, basically. Then if we just adjoin, take our original subalgebra, FW1, and we just adjoin this W, then this is a perfectly good Lie algebra, and it's a one-dimensional extension of FW1. The other obvious one-dimensional extension are those that we get from removing roots. So if we have some root of order 1 of F, then we can divide F by T minus X. And then this is now a perfectly good submodule subalgebra of W1, and it's a one-dimensional extension again of FW1. So these are sort of the two obvious ways of doing one-dimensional extensions. And actually, it turns out that all one-dimensional extensions are of one of those two types. So they either come from derivations or they come from removing roots. And yeah, so the theorem is that if M is isomorphic to this one-dimensional module, so this is a module over FW1. This is a one-dimensional module. Then the dimension of the X group is one. And in this case, the unique extension we get is just the one we get from dividing, just getting rid of this root. And then the other two cases, if M is just a trivial module, then this corresponds, as we saw before, this X group just corresponds to derivations. So it's just exactly, this is just exactly reformulating what I said a few slides ago. It's just the dimension of H1, the H1 cohomology. So it's the degree of F minus the degree of the radical, as we saw before. And then if M doesn't have one of these two forms, then there are no extensions. So yeah, to summarize, the one-dimensional extensions of FW1 are come from either removing roots, so they have this form here, or they are contained in the radical, which come from derivations. And so quite interestingly, even though the one-dimensional representations of FW1, where there are infinitely many, and they're in one-to-one correspondence with a to the power of degree of f, so the deg f dimensional affine space, but actually only a handful of them, only finitely many of them, give rise to non-trivial extensions. So it's quite an interesting, observation. Anyway, thanks to this computation of one-dimensional extensions, we're now able to prove the isomorphism theorem. So that's how the proof of the isomorphism theorem goes. So I guess I should also say that in the motivation part, I also undersold the result. So actually, this holds in more generality than I said earlier. So if we have two subalgebras of finite codimension, which are isomorphic as Lie algebras, then phi extends to an automorphism of W1. Cool. So actually, I guess I should maybe also mention that in the case where we have an isomorphism of submodule subalgebras, when I say that this is an isomorphism of submodule between submodule subalgebras, I just mean as Lie algebras. I don't mean that the isomorphism necessarily preserves their structure as modules, just the Lie algebraic structure. But I mean, then it's a corollary of this theorem that actually the module structure is preserved. Anyway, so yeah, if we have two subalgebras of finite codimension, then isomorphisms extend to automorphisms. And we can do that using our computation of one-dimensional extensions. So that tells us that if we have, I guess I've sort of only told the story for submodule subalgebras, but anyway, then we can indeed, just by removing roots, extend the this isomorphism to an isomorphism in these one-dimensional extensions. And then we can just continue inductively until we end up with an automorphism of W1. Great. And so I just briefly explain how this gives us a computation of automorphisms of our submodule subalgebras. So these rho x alpha are automorphisms of W1, which takes t to the n times del to alpha to the n t minus x to the n times del. So these are automorphisms of W1. And actually, by its proposition of Rudakov from 1986, they're actually the full group of automorphisms of W1 as isomorphic as a group to I guess I should K, yeah. When I say K, I mean C, but whatever. K equals C. It's actually isomorphic as a group to C semi-direct product with C star. And as a corollary of this computation plus our computation or our proof that isomorphisms extend to automorphisms, well, we can say precisely when two submodule subalgebras are isomorphic just by conditions on the polynomials themselves. So FW1 is isomorphic to GW1 if and only if we have f of s equals gamma of g, gamma times g, where s is alpha times t minus x. So we have very sort of explicit conditions to test whether two polynomials give rise to the same Lie algebra structure on the submodule subalgebras. And we can also get the group of automorphisms of FW1. So it just consists of precisely, we take some automorphism of W1, one of these, and we just check whether this automorphism takes f to a multiple of f. And if it does, then it's an automorphism of FW1 if this automorphism takes F to something that isn't a multiple of F, a scalar multiple of F, then it's not an automorphism of FW1. So that's basically a description. Yeah, so that gives a description of the automorphisms. Cool. So yeah, so far what we've done is shown that derivations of subalgebras of W1 are restrictions of derivations of W1. One-dimensional extensions are contained of these subalgebras that have finite codimension are contained in W1, and isomorphisms between finite codimension subalgebras just come from automorphisms. They're just restrictions of automorphisms of W1. So how can we explain this? And so for this, I sort of, yeah, I defined this new notion of which I called completely non-split extension. So we have a Lie algebra L, then L bar is a completely non-split extension of L if it contains L as a subalgebra, and we have a chain of Lie algebras starting at L and finishing at L bar, where the quotient Li plus 1 modulo Li is finite dimensional, and it's an irreducible representation of the previous, this Li. So for example, L2 modulo L1 is an irreducible representation of L1. And this short exact sequence, we require it to be non-split. Okay, so it's just some property. It's basically, I mean, this it looks kind of complicated when it's written down, but it just means we have some chain of Lie algebras starting with L, finishing at L bar, and then we have some sort of property here, which means that we're only considering sort of interesting. Each step is some sort of interesting extension and not just some sort of like trivial extension that we don't really care about. So that's sort of what you should keep in mind. It's just some sort of chain of Lie algebras. Each extension is some sort of interesting extension. Actually, it turns out that in our situation, when we have a actually this doesn't actually this is actually it's actually stronger. The stronger result is that that we just need the dimension of L is infinite. So any infinite dimensional subalgebra of W1 only has, if we have an irreducible finite dimensional representation of this infinite dimensional subalgebra, then it must be one dimensional. So the only irreducible finite dimensional representations of infinite dimensional subalgebras of W1 are one dimensional. So therefore, when we're doing these one dimensional with these, when we have some sort of chain, right, like this, like L contained in L1 contained in L2 and so on, when we do these extensions, then each quotient, so for example L1 mod L, by the definition is supposed to be finite dimensional and irreducible. But thanks to this proposition, actually it's just one dimensional. So we're actually only doing, each step is just a one-dimensional extension. So this is a one-dimensional extension. This is a one-dimensional extension, and so on. So we're just doing repeated one-dimensional extensions. That's all we're doing in our case. I mean, if you're looking at general, general completely non-split extensions of general Lie algebras, then that wouldn't necessarily be the case. But in this particular case, it turns out that because all the irreducible representations are one-dimensional, then we are just doing repeated one-dimensional extensions. And so thanks to this proposition, it turns out that W1 is the universal completely non-split extension of any of its subalgebras of finite codimension. So in the sense that if we have some other completely non-split extension, then L bar embeds inside W1 in a way that makes this diagram commute. And the proof is essentially this proposition from a few slides ago, where I had a similar diagram like this. So it's just sort of, because we're just doing repeated one-dimensional extensions, what ends up happening is that, so if we start with L contained in L1, we just do one extension. This is just a one-dimensional extension. And thanks to the proposition from a few slides ago, this, let me give myself a bit more space. So this is, this fits in a diagram like this. And then L1, we do another one-dimensional extension into L2. And so now this is contained in L2. And thanks to the proposition, again, from a few slides ago, this fits in a diagram like this, and so on. And so we have the chain all the way up to Ln, and then like that. So it's sort of that's sort of what's going on. We have this sort of chain of one-dimensional extensions, and they fit in this sort of chain diagram like this. And this is sort of the summary of the diagram of just sort of the first thing we start with is L0, and the last thing we end up with is L bar. Okay. Any questions about this? Okay. Well, I'll just finish with some further questions that I would like to study. So firstly, I would like to generalize some of the stuff that I've done to other associative algebras or Lie algebras of derivation for other associative algebras. So as I said, if we have any commutative algebra A, then the Lie algebra of derivations is an A module. So we can again study their submodule subalgebras, see if we can get any sort of nice properties like we did for W1. And then the second point is trying to classify subalgebras of the full Witt algebra. So several slides ago, I had this classification, or well, I guess the theorem from a few slides ago was that if L is a subalgebra of W1 of infinite dimensional, then L is isomorphic to a subalgebra of W1 of finite codimension. And the way this was proved was because we had a full sort of coarse classification of subalgebras of W1. And thanks to that classification, it just fell out of the classification that this isomorphism between any infinite dimensional subalgebra of W1 and some subalgebra of finite codimension. And so this theorem is not true if we replace W1 with W, because I mean, for example, W1 is a subalgebra of W, but W1 is not isomorphic to any subalgebra of W of finite codimension. So definitely this theorem as it's written here is not true for if we replace W1 with W, but there might be a way of getting a similar classification like the one Jason and I proved for W1. There might be a similar one for W. And of course, this will not be a corollary of that, but it might still be, I mean, it would still be a very interesting thing to consider. And it might mean that we can extend some of these results that for the full Witt algebra are only true as they stand. They're only true for subalgebras of finite codimension. We might be able to say something in more generality about subalgebras of infinite codimension as well. So that might be interesting. And then the last question is a bit, it seems a bit strange, kind of like it's come out of nowhere. I mean, so the reason why I asked this is because I was looking at short exact sequences like this, where, oh, what do I want to say? I guess it's something like FW1 X M0. And then when we replace FW1 with, I guess we can look at the same thing. So of course, FW1, well, this is contained in W1, and this is contained in the, so this is derivations of the rational functions. So W1 is contained in derivations of rational functions. And so if we look at the image of this short exact sequence under this map here, this inclusion here, then we still get some short exact sequence. And actually, it turns out that this short exact sequence splits. So this splits. So if the injective Hall of W1 or FW1 instead, we can take FW1 instead. Instead in this question. So if we had the injective Hall of FW1 is derivations of the rational function field. So if this is if we can prove that this is an injective representation of FW1, then this would be automatic. So this was a thing that I had to show, and it was kind of annoying to show that this short exact sequence splits. But if we knew this in advance, then this would be automatic. So I thought in the proof where this is necessary to where I needed to show this, it would be nice to know if we could know that this was an injective representation. That would be very nice, and it would simplify the proof a lot. And also the fact that this splits kind of gives some evidence as to maybe this actually is the injective Hall. So yeah. So yeah, that's all I really had to say. Sorry about the multiple typos and stuff. As I said, I didn't have much time to prepare. So anyway, thank you for listening.
Thank you very much. Other questions?
So I have a question. Lucas, so your question, the third question, you use this derivation of the rational field is equal to CT times partial. You use this. This is true, right?
Yeah.
Okay. Yeah. And the second question. Yeah, you basically classified all subalgebras of finite codimension. And for finite dimensional subalgebras, there should be one-dimensional, two-dimensional, and three-dimensional. There are no other.
Yeah, that's right. That's right. Yeah.
Okay. And but that means you know all the, so like the maximal dimensional finite maximal finite dimensional subalgebras of that. Wait a second. This is W. Sorry, this is W, not W1. Yeah. For W1.
Mm-hmm.
Yeah. Okay. So yeah, you want to classify subalgebras of W. Okay. Finite dimension are good. Those are known.
Right. Right. Yeah. I'm more interested in infinite dimensional subalgebras.
Yeah. If you consider infinite dimensional, then. Okay.
Yeah. So I mean, so this is this is related to a work work between Jason and myself from which was it's on the archive. So we did this. This is for W1,
Okay.
and we don't have a result for W. But basically, what we proved was that if we have some infinite dimensional subalgebra of W1, then it can be squeezed. So there's this family. Okay, I guess it can be squeezed between. So I'm not explaining what this notation is, but there exist polynomials f and g such that L can be squeezed between these Lie algebras that I haven't defined. But this is some family of Lie algebras, which these things kind of generalize submodule subalgebras. So they're not, so this LF is not a CT submodule. But it is a CF submodule. So yeah, that's the result. The actual sort of this course classification that Jason and I proved is sort of this. Again, it's sort of like similar to the result of Petukov and Sierra, where they classified finite codimension stuff. It's sort of a generalization of that. That it can be every Lie algebra, every infinite dimensional Lie subalgebra of W1 can be squeezed between two Lie algebras of this family that live in this family.
But besides those subalgebras in W1, yeah, they're two side would be infinity. Then those algebras should be more much, to some extent, should be easier to construct. It seems to me, but we need some details. But there are some other questions. So your results, it would be hard to generalize to Wn. Or if you consider W2, like you consider all, say, infinite dimensional subalgebras or all finite dimensional subalgebras for W2, even for W2. I guess it's hard.
Yeah, that would be hard. I think if I were to try to address bullet point 1, I wouldn't. So for people who are not familiar with the notation, so Taiming was talking about W2, which is derivations of the polynomial ring in 2 variables. So I think instead of trying to do question 1 for something like this, so W2, so instead of trying to go up a dimension, so from 1 variable to 2 variables, I would probably try to study, try to stay in 1 dimension. So try to do something like derivations of Cx, where x is an affine curve. So maybe something like this can be done for question 1. Might be more tangible than W2.
W2 is more interesting because
yeah,
it's related to some other interesting problems.
Yeah, absolutely. I would love to understand subalgebras of W2 better. That'd be really nice.
Okay, yeah, thank you.
Yeah, thanks for your questions.
More questions? Maybe in the chat. Yeah, I have a question. It's about that result by Susan Sierra and Cohomology on some of the subalgebras of W1 finite codimension. So they prove that it is each subalgebra of that type, it is between FW1 and radical FW1, right?
Yeah.
So the question is, is there an example of a subalgebra which is not FW1 exactly? So is there a proper example?
Yeah, okay, I'm having a hard time finding them. Yes, there is. So for example, I'm going to let En be my notation for t to the n plus 1 del. The reason why I'm having this plus 1 is that this makes it, so this, you can think of this as having like degree n plus 1, and this one has degree minus 1. So overall, the total degree is degree n, so that's why it's En and not En plus 1. Anyway, so then the bracket is this. And then if you take, I'm going to write W greater than or equal to n to be the least subalgebra spanned by k, where k is greater than or equal to n. This is the least subalgebra of W1. And another way of writing it, we could also write it as it's a submodule subalgebra. So we could write it as t to the n plus 1 W1. But then we have, so this is a submodule subalgebra, but we could just take W greater than or equal to n direct sum and just adjoin E0, for example, for n greater than or equal to 2. And this is not a submodule subalgebra. Subalgebra. So stuff like this happens.
No, but their theorem classifies all submodule subalgebras, right? So my question was about submodule subalgebras that are not.
Sorry, I didn't understand. So yeah, so all submodule subalgebras are of the form FW1. Yes. Sorry, I misunderstood the question. Yes.
Okay, right. So
yes.
Thank you. So more questions? Okay, so let me thank Lucas again. And so I think okay, I think we can stop now and see you all next week.
Bye.